Alright, AF13, just a quick one this evening to finish off our adaptations to training. I've got your PowerPoint through from Vicky, so I've made some comments and sent that back to you. Last lesson we looked at the adaptations to aerobic training. This evening we are looking at the adaptations to anaerobic training. And anaerobic, as we're all aware, is without oxygen. So resynthesis of energy taking place without oxygen, and therefore our anaerobic training means that we are working the ATP PC systems and the lactic acid system. So we're thinking power athletes, sprinters, athletes that do short bursts of energy over small periods of time, but are working at maximal levels. So key terms for us here when we're thinking about this anaerobic training is the lactic threshold, the lactate threshold, or obla. Alright, so the lactate threshold and obla basically mean the same thing, and they are both the point at which lactic acid is accumulating in the bloodstream. It is therefore being produced quicker than we can remove it. Once we get to that stage, once it's being produced quicker than we can remove it, we move into the aerobic system. And if you remember from our work on energy systems at the start of the year, those processes link very much closely into each other, and that's what we're seeing here. So athletes will choose to work within their lactate threshold, and they will choose to do that because it suits their sport. You know, there's no point Usain Bolt going out and working aerobically for long periods of time. And similarly, Mo Farah, the majority of his training will be aerobic training, but you know, the different athletes, they've got different requirements, and that's why someone would choose to work at this level, because we're aware when we're working within the ATP system or the lactic acid system, our energy is instant. Yeah, there's no delay as there is with the aerobic system. It's instant. We get a stronger muscular contraction, and it's used for power. The other big point, of course, is that for every mole of glucose in the aerobic system, we're getting 38. Here we're only getting 2 moles of ATP from each molecule of glucose. So we've got to be aware of that we are using an awful lot more glucose at this point as well. That's not a reason why someone would choose to do it, but it's a factor. It's a factor in this. Okay? So let's think about the adaptations. Like I said, it's only going to be a short video tonight because we've got some other things that we need to do in the lesson. Adaptations, key one, we get a greater quantity of LDH, lactate dehydrogenase. You should remember that from our aerobic energy system stuff. And that is the enzyme that converts pyruvic acid to lactic acid. It also is used to convert lactic acid back to pyruvic acid. So there's a joint reaction there, a coupled reaction again, as we've seen elsewhere, and that's the enzyme that controls that. And what that means is that once the lactic acid is being converted back to pyruvic acid, we know in the aerobic system the pyruvic acid is the thing that moves forwards to go into Krebs cycle, change to acetyl-CoA if you remember, and it goes into Krebs cycle. So we can utilize lactic acid. We want to utilize lactic acid to get it back to pyruvic acid once we move into the aerobic system. And there's lots and lots of modern research that disputes an awful lot of the stuff from the past, that lactic acid was this terrible substance and it was the root of all evils and cramps and everything else. Now, modern sports science thinking shows that lactic acid is a really important substance in the body because it allows us to transport this pyruvic acid, to store it, and then take it back to something we can use. Increased levels of lactic acid, if we just go back to this lactate threshold, we know once we start getting too much, once we get too much accumulation in the bloodstream and in the muscles, we know that it does start to impact on muscular contraction, lactic acid I'm talking about here, and it does affect some of the reactions that go on in the muscle. It is an acid after all, and it does create a slight imbalance, so it's not a good thing for us to have in our muscles, but it's not the demon that it was always referred to. It actually plays an important part in certain elements of our things. We also have an increased ability to utilise that lactic acid. There's a different point on a mark scheme we have an increased capacity to buffer lactic acid, and buffering is basically the ability to transport it, break it down and convert it back. Right, so it kind of buys us some time, it's not just sat there. And then finally we get this increased ability to tolerate lactic acid. So when we do have large levels of lactic acid in our muscles, it doesn't have as big an effect immediately. You know, our chemical reactions are not slowed down by as a huge amount, and it doesn't have the impact in our muscles. Regular training at this level will increase our lactate threshold, so we will move into that system later. We will be able to work anaerobically for longer, which is an attraction. If I'm a 800 meter runner, for example, a 400 meter runner, you know, the longer that I can work in the anaerobic system, the better, because I'm getting a more powerful muscular contraction. I'm not having to wait for that aerobic respiration to kick in. Other physical adaptations. And these are terms that you will need to be aware of. I mean, we're aware of increased stroke volume, you know that one. Ventricular myocardium. Now, the myocardium, the muscle tissues within the heart, and so therefore the ventricular one are the cells that influence the contraction. If you remember, we talked about the ventricles. We were talking about that last week, and I'm going to show you a little bit more about that in lesson as well. So we get an increased thickness of the fibres, the tissues that control the ventricles, and that the ventricles are what controls the contractions. Therefore, as it says below, we get an increased strength in those ventricular contractions, which we know increases stroke volume, and we also get myofibrillar hypertrophy. Hypertrophy, we know, is a term when something's getting bigger. What you need to be aware of here, the myofibrils are muscle fibres. So all the fibres, you've got fibres within all of your muscles, and they are referred to sometimes as the myofibrils. Those myofibrils are the things that are getting bigger here, which is therefore giving us the cardiac hypertrophy that we talked about previously, the aerobic system, with the heart actually getting bigger itself. So it's these fibres within the muscle that are getting bigger that are having these impacts here. Really short and sweet tonight. It was only 7 minutes. It's dead quick. It's stuff that you can learn the basics of, and then we're going to apply both the aerobic adaptations and the anaerobic adaptations next lesson, where we do a little bit of a comparison task and a discussion point around that, and then also looking at that becoming a 20-mark question. But you've also got to present to me first, which Vicky's going to organise you all with, and I will look forward to seeing you on Tuesday. Thank you.